starting from the beginning of Chapter 6, Mathematical Induction. So we consider a domain D consecutive integers with some smallest starting point. So 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, dot, 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 or negative 2, negative 1, 0, 1, 2, 3, pa, 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 anything of that sort. So consecutive integers with some smallest starting position. It doesn't have to be infinite. Usually it is, but it doesn't have to be. So mathematical induction is used to prove statements of the form for all n. So P of n is a predicate. For all n, P of n is true over domain D. So we start with the first principle of mathematical induction, which is not. So there's a first principle and a second principle. The second principle is really the principle of mathematical induction. This is a sort of simplified principle, which is usually good enough to do the job. Not usually, which is often good enough to do the job. Although the second principle will be necessary later. So to show that for all n, P of n is true, it suffices to show that P of 1 is true, and for all n, P of n implies P of n plus 1 is true. So case 1 holds, and then case n implies case n plus 1. Why does that do the trick? Because given that P1 is true, and P1 implies P2, well, by the truth table for implication, oops, another row. So this is true, true, false, false, true, false, true, false. And then A implies B is, let's just try this again. It's messy. True, true, false, false, true, false, true. So when A is true and A implies B is true, we must be in row 1. Row 1 has A true and A implies B true. These other rows have A false and A implies B true. So we must be in that row, and therefore B is true. So given that P of 1 is true and P of 1 implies P of 2, it gives you P of 2. Given that P of 2 is true and then P of 2 implies P of 3, P of 2 implies P of 3 gives you P3. Given that P3 is true and P3 implies P4, you get P4, etc., etc. So you get P1 and P2 and P3 and P4 and P5 and P6. That's all true. Thus, Pn is true for all. And the basic example of this is the following identity, which perhaps you saw in your Calc 1 class. So show that the sum 1, 2, 3 up to n is n times n plus 1 over 2. So this is the sum in a triangular stack, right? Alright, so like if you ever go to bowling, right, this is a triangular stack of pins, which has got 1 plus 2 plus 3 plus 4. So that's 4 times 5 over 2 equals 10 pins, right? In a stack, triangular stack for bowling. In a triangular stack for 8-ball or straight pool, right? There's 5 times 6 over 2 equals 15 balls in straight pool or 8 ball. And then if you've ever played dominoes in a standard double 6 dominoes, right, there's the numbers 0, 1, 2, 3, 4, 5, and 6 in each spot on the dominoes, right? If you've ever seen these guys, like you can have a 0 and then a 3. You could also have like 3 and 3, or you could have 3 and 6, so on and so forth, right? So for those numbers, you get a triangular stack, right? This is 0, 0, 0, 1, 1, 1, 0, 2, 1, 2, 2, 2, so on and so forth. So how many dominoes are there? Well, there's 7 times 6 over 2 is 28. 7 times 8 over 2 is 28 dominoes in a standard set of double 6 dominoes. So that's what this identity does for you. It's telling you like how many things there are in a triangular stack without actually like adding them up one by one. Did y'all see that in Calc 1? Should have. Do you remember where it was used? I'll leave you to mull that over. Anyway, so we want to prove this is true. The standard way to do it is with induction. You don't have to use induction. There's other ways to do it. So this is the predicate right here. An equation is a predicate. An equation is either true or false. An equation has a left-hand side, it's got a right-hand side, and it's got an equal sign. Okay, well, either the left equals the right, in which case it's true, or the left doesn't equal the right, in which case it's false. So we want to show that that's always true for n at least 1. So the base case is p of 1. So the question is, what does this look like for n equal to 1? Well, 1 plus 2 plus 3 up to n, right, where n, it's the sum of the consecutive integers from 1 to n when n is equal to 1, that's just 1. And this thing, n times n plus 1 over 2, and n is equal to 1, is 1 times 2 over 2 is 1, and oh, they're the same. So then the inductive step, so the first thing you have to do in your inductive step is you have to explicitly write out the inductive hypothesis. So you're trying to show Pn implies Pn plus 1. Okay, so for Pn implies Pn plus 1, you have to assume, for a direct proof, assume that P of n is true, which is usually what you do. Assume that P of n is true, and that's called your inductive hypothesis, right? It's the hypothesis of the implication, so this has got a fancy name called the induction hypothesis. And then you want to prove your conclusion has to be true as well. Assume the hypothesis, prove the conclusion. So show that Pn plus 1 is true. What's Pn plus 1? Well, it's the function Pn with n plus 1 substituted in for n. So this is the sum of the consecutive integers from 1 to n plus 1. And this is n plus 1 times n plus 1 plus 1, which is n plus 2 over 2. All right. Well, the sum of integers from 1 to n plus 1, what comes right before n plus 1 is n. Is n. So I've got the sum of the integers from 1 to n, and then I got my n plus 1 there. Well, we assumed that the sum of the integers from 1 to n is equal to n times n plus 1 over 2. That assumption is called the inductive hypothesis. You got to say, by the inductive hypothesis, you know, this is true. It's got to be used somewhere. So this is n times n plus 1 over 2. This is still n plus 1. And then you do some algebra, and then you get this, which is what you want it to show. That the sum of integers from 1 to n plus 1 is equal to n plus 1 times n plus 2 over 2. All right, and that's what we've got here. So that's the end of the proof. Let's do another example. Similar kind of example. So let's show that 1 plus 3 plus 5 plus dot 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 all the way up to 2n is equal to, does anyone know what this one is? I don't know what the answer to the sum is.
Would it be the same thing, but instead of plus 1, it's plus 2?
This is just the odd ones. That one was the odds and the evens. Oh, so yeah, I see what you're saying. It's kind of like you're going up to 2n, and then you have the sum once, and then you double it. Yeah, I see what you're saying. Yeah, right. So, yeah, that's another proof right there. I like that. I never thought of that. So 1 plus 2 plus 3 plus 4 plus all the way up to 2n. Well, that's equal to 1 plus 3 plus 5 plus 2n minus 1. That's the odd ones plus the even ones. 2 plus 4 plus 6 plus... Oh, no, it's not quite it. Well, yeah, there's a way to do it. This is 2n times 2n plus 1 over 2. Here I can factor out a 2. Plus 2 times 1 plus 2 plus 3 plus all the way up to n is equal to 2n times 2n plus 1 over 2. Oh, so the 2 cancels. So n times 2n plus 1.
Yeah, the 2 on the bottom probably have to be a 4 to compensate for the extra 2 you put in the mix.
Yeah, I like this. Is nice. I like what you do. What's this? We just did that problem. What's this here?
That's a n times n plus 1 over 2.
So these cancel. I have n times 2n. So let's multiply this out. This is 2n squared plus n. So here I got 1 plus 3 plus 5 plus 2n minus 1 plus, this is n squared plus n. It's 2n squared plus n, so those cancel. One of these cancels, so I got 1 plus 3 plus 5 plus is n squared. Nice. I've never thought of that. So you can teach old mathematicians new tricks. Well, yeah, that's one proof. We want to do it by induction. I mean, as an example. But that's another proof that doesn't use induction. It uses the previous problem that this was equal to n times n plus 1 over 2. There's another even more pleasing proof. So it is n squared. But there's another proof that's even more pleasing than this. Is a pleasing proof. I like this a lot. Okay. But there's another even more pleasing proof. Both are more pleasing than the induction proof. Induction isn't always the most informative type proof. Sometimes it can be, but there is an even more. And the answer is suggested by this. What's n squared? Geometrically.
A u?
Well, what else? Yeah, of course, the parabola. What else? N by n array. N by n box of chocolate bonbons, right? which has got n squared. 1, 2, 3, 4, 5, one more, which has got n squared, pieces of chocolate in it. Well, it should be equal to this, and it is. This is 1. There's 3. 5. Oops. 5. 7. 9. 11 equal to 2 times 6 minus 1. There's 36 dots. Neat, huh?
You were right. That is a very pleasing one.
Yeah, that's really nice proof. So I mean, it really gives some. So I mean, the answer turns out to be something that, well, I mean, we're familiar with that trick, right? N squared is the number of dots in an n by n array. So somehow it should be the sum of these odd numbers. Anyway, all of that notwithstanding, so that's a nice little mathematical enrichment right there. Nice mathematical gold nugget. So that's the gold nugget proof. Has anyone ever seen if you've never seen it, I mean, maybe you might get it from the library or look it up from the library. Look at me. You look it up online. It's called Proofs from the Book. And it takes a bunch of sort of basic mathematics facts, and I think this one is actually in there even, and gives the most beautiful proof of that fact. And the book was written in honor of this mathematician, 20th century mathematician named Paul Erdős, who was a very beloved figure. He's the most published mathematician of all time. And he's not just a published mathematician, but the most published mathematician, but he was an ambassador really for the subject, and he cultivated friendships and collaborations with other mathematicians all over the world, and he was like this kind of like really like interesting personality as well. And anyway, he had this idea in his mind that after you pass away, that when you go, this was just what he used to say. Eventually, you'll, when you make it into paradise, you will get to look at the book, and in the book is all the best proofs of all the most beautiful proofs of all the really great theorems in mathematics, and you finally get to look at it. So he would often tell people, like when he was working from them, when they made a good proof, like, oh, that's a proof from the book right there, or something to that effect. Anyway, so that's the gold nugget proof, but let's do an induction proof. All right. So show that this is true for all n bigger than or equal to 1. All right, so the base case is when n is equal to 1. All right, and again, the predicate that we're looking at here, the predicate P of n is equal to, well, it's that statement itself. It is this equation itself. Either that equation is true or that equation is false, given a certain numbers n. Like P of 1 may be true, maybe P of 3 is false, or P P of 17 is false, or something like that. Okay, but we're going to show it's always true. So the base case is when n is equal to 1. So when n is equal to 1, what does the predicate mean? What does P of n mean? 1 plus 3 plus 5 is consecutive odd numbers up to 2n minus 1. So the consecutive odd numbers from 1 to 2n minus 1. Well, what does that mean when n is equal to 1?
That the whole answer should be 1.
It's just 1, yeah.
The n squared.
And then n
1
squared, right, and that which is n squared as well, and then n, I like to do it this way. And then n squared, well, that's 1. And they're the same, right? So that's great. Right? This left-hand side of the equation is 1, and this right-hand side of the equation is 1, when n is equal to 1. Now, inductive step. The inductive step is that Pn implies Pn plus 1. Okay, take your inductive hypothesis. Assume that 1 plus 3 plus 5 plus 2n minus 1 equals n squared for some n in the domain that we're talking about. This is sometimes important. It's not always, but sometimes. So we're talking about all n bigger than or equal to 1. So some n within that domain. So for some n bigger than or equal to 1. We're talking about all n's bigger than or equal to 1, so this is true for some unspecified n that's at least 1. We do know so far it is true for n equal to 1, but now we're just picking some other n where it might be true, hypothetically. The induction hypothesis. Hypothetically, it might be true. And now we want to show that Pn plus 1 is true. So this is Pn. This thing right here, that's a function. It's a logical function. It's a function from the integers to the set true, false. So what does that function look like when n is replaced by n plus 1? Well, it's the sum of the odd numbers, 1, 3, 5, up to, and what's this? When n is replaced with n plus 1. What's the next number in the stack?
2n.
2n? Right, we're replacing
2n.
n with n plus 1.
N. So yeah, just 2n, right? Or 2n plus 1?
Hold on. So 2n, I can put this parentheses here, is going to be replaced with, so I'm going to replace this n with n plus 1. So it's going to be 2 times n plus 1 minus 1, which is 2n plus 1, right?
Yes.
Yeah. So, another clue to why that's the answer is that we're using odd numbers, right? That's an odd number, and the next odd number in the sequence is this one. 2n minus 1, 2n plus 1. They go by 2's, right? So this should be equal to what? Replace n with n plus 1, and you get
n squared 2n plus 2.
Plus 1. Yeah.
I was factoring it out. But wait, yeah, plus 1.
Oh, right, yeah, still plus 1 at the end there. But anyway, n plus 1 squared. Just leave it at that for now. All right, so let's start with this. Well, 1 plus 3 plus 5 plus 2n plus 1. So that's the sum of the consecutive odd numbers from 1 to 2n plus 1. What's the odd number that comes right before 2n plus 1? What's the odd number that comes right here?
2n minus 1?
2n minus 1. Right? So just sort of filling in the dot, dot, dot a little bit, we know that 2n minus 1 is there, which, by the induction hypothesis,
would just be n squared, correct?
be n squared. is equal to n squared plus 2n plus 1, which is equal to n plus 1 squared. And that's what we wanted to show. Okay, so that's a nice example. Let's see what else we've got. Hold on. Yeah. Let's show that. Oh, not this one. Hold on a second. Yeah. No. Oh, yeah, this will work. Okay, so another example. Let's do one of the inequality. So let's show that n factorial, you all know what n factorial is, right? I'll explain it in a moment, is bigger than 2 to the n for all n bigger than or equal to 4. Okay, remember, okay, n factorial is n times n minus 1 times n minus 2 n minus 3, 3 times 2 times 1. So n plus 1 factorial is what? N plus 1 times
n minus 1.
Times n. Get it down by 1 each time.
Times n minus 1.
Yeah, times n minus 1 times n minus 2. Right. So n plus 1 factorial is equal to, actually, n plus 1 times, what's this? It's this right here.
N factorial.
N factorial. So that's a little something that helps you do induction with factorials there. N plus 1 factorial is n plus 1 times n factorial. So, for example, like 1 factorial is 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 factorial is 6, 4 factorial is 4 times 3 factorial is 24, 5 factorial is 5 times 4 factorial, which is 120, 6 factorial, 6 times 5 factorial is 720, etc., etc., etc. Okay, so we want to show that n factorial is bigger than 2 to the n for all n bigger than or equal to 4. So in this problem, the predicate Pn is the inequality. N factorial is bigger than 2 to the n. Notice, right, we're doing n bigger than or equal to 4, right, because P3 right, 3 factorial is bigger than 8 is what?
Incorrect.
Is false. Right, so these predicates that you're using in your induction proofs they're not always true. right? They're false. This one only starts being true at 4. 3 factorial is 6. 6 is not bigger than 8. All right, so the base case here is when n is equal to 4. All right. Oh, we got it right here. Okay, so the base case is when n is equal to 4. All right. Well, in the base case, n factorial, right, is 4 factorial, which is 24. Right? 4 times 3 times 2 times 1. And 2 to the n is 2 to the 4th, which is 16. Right? And yeah, 24 is bigger than 16. So you're good to go there. Base case. Induction step. Right, is we want to show Pn implies Pn plus 1. So we need to assume what? Assume that the hypothesis, your induction hypothesis, is true. What's the induction hypothesis going to be? Right, you have to assume Pn is true. We don't write Pn, predicate. We write what Pn means. Not for all, it's specific for some. So assume that 2 to the, you want to show it's true for all n, or sorry, assume that n factorial is bigger than 2 to the n for some n in your domain. What's the domain? Again, n's bigger than or equal to 4. So you're trying to show it's true for all n bigger than or equal to 4, so you can't assume that n is bigger than or equal to, you can't assume that it's true. Right, so this is not a valid proof technique, right? Prove that, pigs fly south for the winter. Well, pigs fly south for the winter, therefore it's proven, right? You can't just sort of state it. So for some n in the domain, show that what? Pn plus 1 is true. And what's that going to look like? This is Pn. What's Pn plus 1 look like? All right, replace n with n plus 1, and what do we get?
N plus 1 factorial and 2 raised to the n plus 1.
All right, it's true as well. Okay? All right. Well, I'm teaching you. No, thank you. N plus 1 factorial. Okay. Well, like we were saying before, it's n plus 1 times n factorial. The induction hypothesis says what? That n factorial is bigger than 2 to the n. Of course, n plus 1 is positive. So by the induction hypothesis, we get what? n factorial is bigger than 2 to the n. So n plus 1 times n factorial is bigger than what? Yeah, it's bigger than 2 to the n, but more than that.
Bigger than 2 to the n times 2.
More than that.
Times n? No.
More than that. Right? I mean, if x is bigger than 12, something like that, then 7x is bigger than what?
7 times 12.
Yeah, 84. Right? So here we have x. Right? So x is bigger than y. So then z times x is bigger than z times y.
N plus 1 times
N plus 1 times 2 to the n. So by the induction hypothesis, right, n plus 1 times n factorial is bigger than n plus 1 times 2 to the n. Right, here, this is, right, a is bigger than b. So when c is a positive number, c times a is bigger than c times b. Right, so here's a bigger than b. So here's c times a bigger than c times b. Right, well, what's n plus 1? N plus 1 is bigger than or equal to what?
Four.
Right, so n plus 1 is bigger than, well, okay, 4.
5.
5, yeah, all right. That's fine. 4, if you go 4 there, it's totally correct still. Is bigger than 5 times 2 to the n, which is bigger than 2 times 2 to the n, which is 2 to the n plus 1. As required. Right? By the way, when you're working with inequalities, okay, so like I've been kind of trying to impress upon you guys that when you're working with equations to always work in a chain, or when you're working with equivalences to work in a chain and not in a stack. Right? Don't stack your expressions. If you're working with expressions, okay, work in a chain. Unless you're trying to solve an equation. Stacking equations is when you're trying to solve equations. This isn't solving an equation. Solving an equation is when you got 7x minus 5 equals 22. That's solving an equation. Find x. So then 7x is 27. So x is 27 over 7. Okay, so here we're stacking. This isn't that. Okay, we're doing a comparison. So we're doing an evaluation. You should work in a chain. Now, when you're working with equalities or with equivalences, logical equivalences, you can stack it and you can get away with that. It's less elegant and takes up more space, but it still makes sense. With inequalities, not so. You cannot stack inequalities and ever expect it to make sense. It simply doesn't. Okay, you have to work in a chain. Right? And when working with inequalities in a chain, right, all inequalities symbols must point in the same direction. So in this case, they're all pointing to the right. Right, I mean, this, like here, if I was to do something like this, n plus 1 factorial, bigger than 2 to the n plus 1. Like, so here's something, like here's like an attempt at stacking things. Right, and we sort of questioning, is that true? Is that true? So by hypothesis, induction hypothesis, What's that mean? What did I just do there? If you're confused by that, it's because it simply doesn't make any sense. If you're confused by that, it's because it simply doesn't make any sense. Because I've got that this is less than that, and I'm trying to show that this is bigger than that, but because this is smaller, I can show that this is bigger than that. That just doesn't make sense, okay? And if it did make sense, it's only by that chain of logic that I just said, which is way too complicated to just go without saying. It doesn't go without saying. Okay, this says exactly what needs to be said. Says exactly what needs to be said. When you're working with a chain of inequalities and all the inequalities point in the same direction, so you got like A is equal to B is equal to C is bigger than or equal to D is equal to F is bigger than or equal to G is bigger than or equal to H. This implies A is bigger than or equal to H. Okay, bigger than or equal to because there's no strict inequality going down at any spot. If there was just one strict inequality, you actually did go down, in which case you can conclude A is bigger than H. All right, so all the inequalities got to point in the same direction, and as long as you have one strict inequality in the chain, it gives you strict inequality for the beginning and the end. Okay, when working with inequalities, you have to go in a chain. Okay, so when you go to real variables, you're going to do a lot of stuff with inequalities, so you got to work in a chain. Okay, so I took up too much of your time. I apologize. So we'll see you guys on Monday. Please take a look at the homework and come with some questions on Monday, and we'll do some Q&A before we start lecture again.